And the idea here is we're going to look at the power rule first. You could take your definition of the derivative and find each of these derivatives. And the x squared one, by plugging in the x plus h, wouldn't be bad. And I think we've done that one before. And you get 2x. You could also do x cubed, and it would be a little bit bigger. We've done some with x cubes, and they cause us to multiply things out. And you would get 3x squared. And if we keep doing these ones and look at what happens, write them all down here, we start to recognize a pattern. So I'll give you a moment to look at each of those and see if you can see the pattern. Some of you know the pattern already of what is happening. So that is the pattern if we take another one, if we take 9x to the negative 5. Again, we're going to subtract 1 from the exponent. And when you subtract 1 from negative 5, you're going to get negative 6. And we think like that negative 5 comes in front, multiplies that 9, and you would get negative 45x to the negative 6. Is this a lot quicker than the definition of the derivative? Yes. When I said before you'd be able to do it within 3 seconds, I wasn't lying. It is that quick. And so this is our first pattern. Now, the interesting thing is it works even with some situations that we're not used to, like the square root of x, because you can change the square root of x to x to the 1/2. And sure enough, you can bring the 1/2 in front and subtract 1 from the exponent, and that's the derivative. And no more need to multiply by the conjugate to rationalize the numerator. If you use the definition of the derivative, you would have to do that. Just a constant, 5. We could rewrite that as 5x to the 0 and do the same thing. What would happen? The 0 would come in front. 5 times 0 become 0, and it wouldn't matter what the exponent was anymore. It'll just be 0. 7x we can think of as 7x to the 1. And if we use the law, the 1 would come out in front, subtract 1 from the exponent, we'd get 7x to the 0. But how do we write 7x to the 0 normally? Just 7. So here we have a cube root of x. We can write that as x to the 1/3. The 1/3 would come out in front, subtract 1 from the exponent. And so the main skill we are going to practice today is subtracting 1. Hopefully you get really, really good at it. Okay, so we get to subtract 1 in all sorts of different ways, from fractions, so 1/3 minus 1 to get negative 2/3. What would we do with this one? How could I write this as an exponent? X to the negative 1/2. Right? Because an exponent on the bottom of the fraction, we can always move, if we take one extra step here, agree that this is x to the 1/2 on the bottom, and you can always take an exponent and move it from the numerator to the denominator or denominator to the numerator by just using the negative exponent law, which just makes your exponent negative. So the fact that this x to the 1/2 is in the bottom of our fraction, we can move it to the top of our fraction by making it x to the negative 1/2, and then bring that number in front, subtract 1 from the exponent, and you get x to the negative 3/2. So from this, we can make some basic ideas. We have a constant rule. That's whenever you have a number by itself, the derivative of that number will be 0. So the derivative of y equals 5 will be 0. Doesn't matter what that constant is, the derivative is equal to 0. And the power rule says that any time you write y equals x to the n, where n is any real number, then the derivative, that n value comes out in front, and if there's a number out in front, it would multiply by that, and then you subtract 1 from the exponent. Now, This works for all real numbers n, and I'll introduce you to some new math symbols. You probably know that means real numbers. Sometimes in math, when we don't want to write for all because that would take too long, right? Because it's 6 letters, like, wow. You can write an upside down A. Very helpful. We won't use that very much. But I'll introduce you to some interesting math terminology. Like, here's another fun one. Ooh, if. Does anyone know what if stands for? It stands for if and only if. That's like really big if. Then you say if and only if. And we'd use that mathematically in proofs sometimes when you wanted to say, well, this is true, not just if this happens, but if and only this, if this was happening. Like it's really contingent on that. Then you can use the extra F for if. Anyways, so those are some fun things there. And then, of course, there's the constant multiple rule, and we saw that when we had a function like 3x squared. Having that 3 out in front doesn't matter. We know that if we just had x squared, that the derivative is 2x. So having that 3 out in front, that 2 will just get multiplied by that 3, and you just get 6x. But this gives you a sense of what it looks like to write out these rules in general terms. Because if you're taking university classes and sometimes you're unable to understand your professor and you're not sure, and you go back to your textbook and your textbook shows you something like this, then you might feel like, well, I'm not able to understand my professor, I'm not able to understand my textbook, then I'm in trouble. So it's important to realize, what are they trying to say? They're trying to say here, if you have a function, g of x, and it's equal to 3 times x squared, which is what we did here, had some number out in front of a function that we know, then the derivative is equal to 3 times the derivative of x squared, which is 2x. That's the idea that they're showing here. Now, you're going to be able to do these so quick that you won't think that step. You'll just bring the 2 out in front and multiply by the 3 and write 6x right away. But if you're ever going back to a textbook and saying, well, what are they trying to show? A good way of looking at a general case is to start off with something that you do know how to do. So I say, okay, I'm going to make a function. C is some kind of constant, so I'll pick a number for that. F of x is another function. I'll just choose a function and then see what does it mean if I do the derivative. And for something like this, if you read this in a textbook after learning calculus in high school, you would go, oh, I knew that all along. I just didn't realize what they were trying to say. All right, so let's do a couple examples. Start off with an easy one. Again, I'll try to change up the notation as we go through here. It says find dy dx, so it wants this kind of notation for the derivative. Did you get negative 15x to the 4? Yes. So another way of asking to find the derivative is differentiate with respect to x. So this is just another way of saying, can you find the derivative? So if I made y equal to this function, can I find y prime? Well, before I can work with this function as it is, my x to the 8 right now is on the bottom of my fraction. My power rule works for any x that's in my numerator. So I'm going to have to first take this function and rewrite it with something that looks like I can do my new power rule with. Can you see what I did? I took the x to the 8th, which was in the denominator, used my negative exponent law and said, well, an x to the 8 in my denominator is the same as an x to the negative 8 in my numerator. Now when I bring that negative 8 in front, you're going to have to multiply it by 3/4. How do you multiply negative 8 by 3/4? Well, how do we multiply fractions? Negative 8 is really negative 8 over 1. So can you see that you're going to get negative 24 over 4, which is going to simplify to negative 6? Or maybe you simplified the 8 over 4 first and got 2, and 2 times 3 was 6. Yes. That's a good question. Why didn't I take, when I have this, why is it not equal to this? Okay, that's a good question. Why does the 4 stay in the bottom of the fraction? Well, the reason for that is right now this 8, that's an exponent only to the x. That exponent doesn't go to the 4 as well. Does that make sense? This is different than this. So when I write it as 1 over 4x to the 8 and the 4x is in brackets, that means that the 8 exponent goes to the x and to the 4. And this one would equal 4x to the negative 8. But in this case, this exponent of 8 is only to the x and not to the 4. So when you change with your exponent laws, only the x to the 8 would move to the top. Similarly, it's probably even easier to see if you had 2 sets of variables. Could you see in this one that only the y cubed would move to the top and become positive? The x squared wouldn't move with it. It's a little bit easier to see sometimes when you have more variables. It's the same idea with that 4. That 8 only hits the x, so only the x to the 8 would move to the top. So anyways, we've multiplied that 8 in front. When you subtract 1 from the exponent, this is where you're going to make mistakes subtracting 1. You're so good at subtracting 1 that if someone says, what's 8 minus 1, you'll say 7 so fast that sometimes you won't even think about it. That when you get negative 8 subtract 1, you are going to be tempted to write negative 7. Can you see yourself being tempted to do that? So you have to remember, negative 8 subtract 1 is negative 9. And there we have our derivative. Another way of asking to find the derivative is by having this notation out in front of a function, d dx. So the d dx means find the derivative of whatever's inside with respect to x. Now we know that it's with respect to x because there's a dx on the bottom. Technically, we could choose different variables. You could find dda of a squared, and it would just be changing the variable from x to a. We tend to use x a lot with derivatives, so you sort of get a sense of ddx or dy dx because you use y and x. But later on, as we do applications, with respect to time, then we'll be doing d dt. And we'll be doing different derivatives with different variables. So it's important at the beginning to realize we can do different variables and what the variable on the bottom means that you're going to be doing the derivative with respect to a here or with respect to x. In this case, your derivative would be, bring the 4 out in front, times 7 is 28, x cubed. So what we're going to find is we're going to be using our exponent rules a lot, because in we have a function with our exponent rules, we need to be able to change radicals to rational exponents. So when you have a cube root of x squared, do you remember that a cube root is the same as to the power 1/3? A fourth root is the same as the power 1/4, and so on. Now, most of you will be able to go directly to x to the 2/3 in this case, but I just wanted to point out that a cube root is to power 1/3. And then what is our exponent law when we have a 1/3, a power to a power? That's where we multiply, and 2 times a third will be 2/3. It's still not in the form that we can do our power law with. We have to move that x to the 2/3 to the top of our fraction. Again, the 3 will stay on the bottom, and now when we move that to the numerator, it'll be x to the negative 2/3. Yes? Well, but I've gone from here, which has a 2/3, because I multiplied x squared time 2 times a third to put that as a single exponent. Yes? The 3 here doesn't get affected by any of the exponents. It's a coefficient in front that's multiplying by that. Okay? And now that we've taken the time to rearrange it, now we can bring the negative 2/3 out in front. Our derivative, 2/3 times 7/3, negative 14/9. And again, you're going to get good at subtracting 1. So these are the hardest ones where you have to work with your radicals and use all of your exponent laws. Now that you've been able to see how you can get it into the form that it's as a power in the numerator, then you can apply the power law and solve. We got a couple questions here to end with, saying if I gave you the answer, could you work backwards and say what we started with originally? So if I told you the derivative was 5x to the 4, what function would we have had to start with? X to the 5. And we're going to find out later that this isn't the only function that has the derivative of 5x to the 4. We're going to learn that you could have also had x to the 5 plus 3. Because what's the derivative of 3? 0. And we're going to find out later that we could take both of those derivatives separately, and so the derivative of this one would also be 5x to the 4. Or we could have had x to the 5. Anybody have a favorite number that hasn't been used for a while in a math class? No favorite numbers out there? 7? Okay. Positive or negative 7? Negative 7? Oh, nice. So that also would give us a derivative of 5x to the 4. What's that? Well, infinity would work, although it's technically not a number. But you could, you know, do that number, and it would work as well. So it doesn't matter. In fact, what we will learn later on in units, that we could have any number there, any constant. We'll use a big C for constant right now, because any constant there when we take the derivative working backwards would give us this. You could even use 1.9 repeated if you wanted to. So here's another one. The derivative is given. For x cubed. So you start to notice that what you're doing is you're working backwards. Instead of subtracting 1 from the exponent, you're adding 1 to the exponent. And then you're trying to figure out, well, what number in front would give us that. And in this case, it would have to be a 4. Or you could have 4x cubed plus c. Sure. Plus any constant. And that would work. So here are some questions that you can try. And we'll take the last 10 minutes to do that.